Find the eccentricity in the column in inches. In this problem, a 20-inch by 20-inch doubly reinforced square column is eccentrically loaded. The Young's modulus, compressive strength of the concrete, and yield stress of the steel are provided. We also know that the strain in the tension steel equals the yield strain, and we've been provided the area of steel for both the tension and compression sides of the column. Since we're analyzing an eccentric column load, we'll define the width of the column, B, and the height of the column, H, as shown in the figure. The nominal moment developed in an eccentrically loaded column equals the nominal axial load, Pn, times the eccentricity, E. Therefore, the eccentricity equals the nominal moment divided by the nominal axial load. We'll first solve for the nominal axial load, Pn, which equals the compression force in the concrete plus the compression force in the compression steel, minus the tensile force developed in the tension steel. The compression force of the concrete, Cc, equals 0.85 times F prime C times A times B, where we already know the compression strength in the concrete, F prime C, and the beam width, B. The length A equals beta times C. And from the problem statement, we know beta equals 0.85. To solve for the length C, we'll use strain compatibility. From the figure, we know the strain in the concrete, epsilon C, is to the length C, as the strain in the tension steel, epsilon S, is to the length D minus C. Solving for C, we get C equals D times epsilon C divided by the quantity epsilon S plus epsilon C. From the problem statement, we know D equals 17.5 inches. Also, as is typical, we'll set the strain in the concrete equal to 0.003, the strain at which the concrete is assumed to crush. The problem also states the strain in the tension steel equals the yield strain in the steel, which equals the yield stress in the steel divided by the Young's modulus of the steel. Both of these values were also provided in the problem statement, and the strain in the tension steel equals 0.00207. After plugging in the length D and the two strain values, the length to the neutral axis, C, equals 10.36 inches. Now we can solve for the length A, which equals 0.85 times 10.36 inches, or 8.80 inches. Now we can solve for the compression force in the concrete. We plug in F prime C, A, and B, and the compression force in the concrete equals 5.236 times 10 to the 5 pounds. Next we'll solve for the compression force in the compression steel, CS, which equals the area of compression steel, AS prime, which is 7.5 inches squared, times the stress in the compression steel, which equals the minimum value of the yield stress in the steel, Fy, which we know equals 60,000 pounds per square inch, and the product of the Young's modulus and the strain in the compression steel. We can determine the strain in the compression steel, epsilon S prime, by returning to our plot, which shows the strain profile in the column. This time, we'll relate the strain in the concrete to the strain in the compression steel, where the strain in the compression steel equals C minus D prime times the strain in the concrete, all divided by C. Plugging in the appropriate values, the strain in the compression steel equals 0.00227. Plugging this value in for epsilon s prime, the stress in the compression steel is the smaller of 60,000 pounds per square inch and 66,005 pounds per square inch, which is 60,000 pounds per square inch. Returning to our equation for the compression force in the compression steel, this compression force equals 4.5 times 10 to the 5 pounds. Lastly, we have to solve for the tensile force in the tension steel, TS, which equals the area of tension steel, 7.5 inches squared, times the stress in the tension steel, Fs, which equals the yield stress of 60,000 pounds per square inch, because the problem states that the strain in the tension steel equals the yield strain. This makes the tensile force in the tension steel equal to 4.5 times 10 to the 5 pounds. Now we can solve for the nominal axial force, Pn. It turns out that the tensile and compressive forces in the steel cancel each other out, and the nominal axial force, Pn, equals 5.236 times 10 to the 5 pounds. Returning to the original equation for the eccentricity, E, we have just solved for the axial force, Pn. Next we'll solve for the moment term, Mn. If we take the moment through the center of the column, h over 2, the nominal moment includes a contribution from the concrete in compression, the steel in compression, and the steel in tension. If we plug in these forces and plug in the lengths of D, D prime, A, and H, then the nominal moment in the column equals 9.682 times 10 to the 6 pounds inches. Plugging this moment in for variable Mn, the eccentricity in the column equals 18.5 inches. When reviewing the possible solutions, the answer is B.